like teacher tried to teach something. I heard math was broken. It's like, now's not the time, Kirk. Your teacher's just trying to teach you multiplication tables. Okay. Notes out, please. Notes out. Oh, I've got a handout. Lovely handout here. Why is this? Don't do this to me. There we go. What? No, it's on here. I totally forgot to do that, and you asked me to. I can do that if you remind me. I only just printed them out. And this is, but it's also just for your reference. After we spend all that time drawing last day, I wanted you to have nicely drawn colored versions, just so you had a reference. You do still need to know how to draw which ones. Like, which one will I ask you to draw in if I gave you an assessment? Yeah. What's the simplest one called? S. And then the next one was the right, sorry? You didn't get one? She's hoarding them. Oh! Thought I would open up with this. Hold it. Before I begin, there may be some slight swearing. Is everybody okay? Is there anything not okay with some slight swearing? Or should I ask, is it a bones or no bones day?
What day is it? What day is it today? I didn't check. Is it bones or no bones?
I saw it and I was like, oh great, it's a bones day, and it wasn't. It was someone like commenting and replaying it, so I haven't seen it yet today. Yeah. And the reason I bring that up is because we can actually answer it now. Previously, I've answered it for you, and it's a lie. What's the lie I told you? Why can't your hand go through the table? No, that's not actually maybe I didn't tell this class. Someone asked it. I thought it was this class. And there is a traditional answer that's given, yeah? Right. Well, atoms never touch. And what's the reason atoms never touch?
No, because of electrostatic repulsion.
Right. Because you have negative electrons on the outside of every atom, and those repel the atoms of here, and so you never touch. And that was the explanation up until 1967, before quantum. After quantum, it wasn't the explanation anymore. Because that explanation makes no sense. That explanation, is your hand charged? No. It's electrostatically neutral. Despite the fact there are protons and neutrons, even if there's electrons on the outside, it is mostly empty space. And electrostatic repulsion is not strong enough to keep your hand from going through the table. You're more nothing than something. Yeah, absolutely. However, we last day, where is it? I want our diagrams from last day. Oh, there we are. Last day when we did, hold it. Did we not save it? We did those. We did the d orbitals, didn't we? Yeah. I did them there, and I think I skipped over a picture because I did them on a different page. Never mind. So I just need to go down. Yeah, and we did our own. We did all those. Excellent. So I'm just going to use this page because that's what I just gave you. And every atom looks like this. It has a nucleus. It has an s orbital, so it has the s. But if the p is filled, it has all of them. So it has this, and it has that. Now, drawing it all together gets a little you're not drawing this, are you? No. Okay. How many electrons fit in each orbital? In every suborbital. How many fit in the s? 2 electrons. When the energy level is equal to 1, when n is equal to 1, only 2 electrons fit in the first shell. That's an s. When n is equal to 2, we have the 2s, and then the 2px, 2pz, and 2py. You get 2 electrons, 2 electrons, 2 electrons, and 2 electrons. And we're about to do a little bit today, and so this is new information. Not only do those 2 electrons fit, they only fit in one way, something called the Pauli exclusion principle. There is an incredibly strong force that keeps electrons apart if their spins are the same. So electrons only fit in a particular configuration that we represent with that. That is spin up and spin down. Only 2 electrons fit in here. Only 2 electrons fit in here. Only 2 electrons fit in here. This is a stronger force than electrostatic repulsion or attraction. And once these are full, and every atom has full shells, you cannot get through that. So it is not an electrostatic repulsion, but as some people were guessing, it's due to quantum. And when these orbitals get against each other, the electrons can't fit into each other's orbitals because they're already full. And that keeps everything apart. And that is the only thing keeping everything apart. It's called the quantum force. Oh yeah, then we'd all go, and we would actually just all fall together. Probably all that mass in one spot. Yeah, because the mass wouldn't go anywhere. Although mass actually doesn't really exist in another way. Like, it's not an inherent property of matter. It's just when you move through space and you have a particular wiggle, it drags, and that acts like mass. We have no idea what happens inside a black hole because the laws of physics literally stop at the edge. And it's not that there isn't something or that it doesn't apply, it's that we can't predict what happens because all of our physical laws can't say what happens at those extremes. Yeah. And as far as we can tell, time essentially stops inside a black hole. So if you manage to get inside one, the entire age of the universe passed while you were there for a second. Like, it was just gone. That just comes out of relativity. Interstellar, yeah. That planet they were on, yeah. Spoilers for Interstellar? Anybody not want spoilers for Interstellar? There's a planet going around a black hole, so it's in an area of a gravitational field. When you're on the planet, time is traveling slowly. Yeah, so when you hear the music, they time the music so that every beat of the music is a day passing on Earth. So as they're walking around, it's just days going by. And that is something that does happen. Like, our satellites going around the planet, because they're moving, have a different sense of time than we do. We have to adjust for that for our telecommunications that rely on precise timing. We can measure that effect. Yeah, it is. We can time travel now. I have a time travel device, that travels in both time and space. I get into it, and I drive to Victoria, and when I get out again, it's an hour later, and I'm in Victoria. Now, if you want to travel forward in time faster or slower compared to other people, yeah, you can. You can manipulate that with gravity or speed. So if you take a little particle that has a decay of, say, 20 minutes, and you put in a particle accelerator and you speed it up near the speed of light, you'll notice its decay is no longer 20 minutes. It's like an hour. You changed its sense of time. Relative to you, it's aging more slowly. But relative to it, you're aging more quickly. That's why it's called relativity. Einstein's theory of relativity was because time was relative to your motion. The faster you run, the more your mass will be, the longer you'll get, and the slower time will occur for you. All three of those things happen. There's length expansion, there's time dilation, and there's a mass increase. So if you got on a rocket ship and you slowly sped up to like 99% the speed of light and you just orbited the Earth for a while, time for you would pass normally, but a year for you might be 1,000 years on Earth. From Earth's perspective, time is, like, your communications would be like, it's like the whales in Finding Nemo where they talk slowly and deeply. Like, all of that would be going on for you. You would think you're talking normally, but when they talk to you, they'd be like, and be extremely quick. Yeah. So if there were civilizations, like, say it's possible to have molecules on the surface of stars, like some sort of stellar chemistry that occurs, those reactions would happen extremely slowly because of the gravitational pull at the surface of the star. They would happen really, really slowly. Yeah. Hold it. Yeah, that should be it. Anyway. We are doing, yes. Is the same concept what? Sloths? Oh, no, that's just their metabolism. So that's biology. They're slow because they're essentially hibernating all the time. If you get them in the wet season, they can rip you apart and they move really fast. They swim around with their forest flood, apparently. That might be their metabolism. Like, in the morning, fast people are irritating. That's just your body's perception of time, which is a completely different type of time dilation. Pardon? How do we know relativity works? It is measurable. The orbit of Mercury that is also like how fast your neurons fire and how well your brain is working can all affect your sense of time. That's a sense of time. That's not the chemical reactions occurring at a particular rate. So we can have an objective measure of time based on, say, half-life. And we can say that speeds up and slow down. Then we can have a subjective measure of time. I'm doing something really fun, like learning electric structure for orbitals, and the time just flew by. That's different, yes. No, that's just the subjective measure of time. You're not going any faster. Mercury rotates fast enough around the sun that its time is very slightly different than the other planets. They're going more slowly. And that actually bothered Newton, because when Newton predicted using his laws, Mercury was always out of sync. You couldn't exactly predict it. You had to introduce a fudge factor. It bothered him. And it wasn't able to be explained until Einstein said, actually, time is moving differently from Mercury because it's orbiting faster. Yeah. And our satellites move fast enough and make small enough adjustments that we have to adjust for that with our telecommunications. So our phones have built-in formulas to deal with relativity. Why does it have a higher speed? Because it's... Yeah. If you calculate the gravitational constant using Newtonian, like the laws, G1, G2, like that, I can't remember the exact formula, Mercury comes out slightly off to the measured value. It is moving at a different speed than it should be. Yeah. Okay, I'm going to write this down. And you can't see it. At least not all of it. Write the title. This is the real electronic structure. No, it's still useful. 288 will work in some areas, but we're going to now do quantum. The order matters, and I've color-coded it so you can clearly see it. You can label it and have all pencil in the same color, but this is the amount of energy in each energy level. This is the first energy level, the second energy level, the third energy level, the fourth energy level, and the fifth energy level. 1, 2, 3, 4, 5. We're going up to 5s. So the first energy level only has one s. The second energy level has both s and p. The third energy level has s, p, and d. The fourth energy level has s, p, d, and f. So as we said, as you go up in energy levels, you get more sub-levels. So each one has it. The spacing matters. 1s and 2s. 2p should be above 2s. 3s, 3p, and 3d should all be above each other. 4s should be between 3p and 3d. It should be right here. Five s should be between 4p and 4d. It should be right there. So I'm going to erase this afterwards, but it should be about there. Oh, I'm just giving you the relative size. 5s should be between 4p and 4d. So you need to put it in here. Now, I don't care if it's like, oh, that's 2/3 up. I mean, if it's halfway, fine. Just make sure it's not above it. Yes. 4s should be a little bit below 3d. And these are still what we did last day. This is the s orbital. Oh. Why don't I color code it? You don't have to write this down, but this is the 2s orbital. It should be slightly bigger. And we have the 2p, which has our 3 p's. Boom, boom, boom. So we have our s orbital, our 3p, and then our d. So the orbitals have shapes, which is what we did last day. In the first shell, you have a ball. In the second shell, you have a ball and 3 dumbbells. In the third shell, you have a ball, 3 dumbbells, and then the butterflies with the weird one with the ring, hula hoop. Because when you're out dancing with the butterflies, you would also have a hula hoop. Image always comes, whenever I see those, it's always an image in my mind, and someone's out in the field and they're hula hooping, and then the butterflies are flying around. Now, do we need that for this? No. Linking it to last day, but these are what we're filling. So when I say electrons go into here, I'm filling a sphere. And now I'm going to erase these shapes because we don't really need them right now unless anybody objects. No objections, yes. Our example will be calcium. And we're going to do neutral calcium. All of these so far are going to be neutral. And I'm just going to ask a random person, have your periodic table out. What is the number of electrons in calcium? I should probably do attendance. Brooklyn, Kaylee, Chet, Davis. Davis? Yeah, there he is. Denzi, Dylan, Francois, Heather, and Jaden. Jaden's missing. Jonah. Jaden didn't move over anywhere, did he? No. Jonah? Jonah's also missing. Kate? Oh, she's in the other class. I accidentally added her. I still got to remove her. Lillian. And Lucy. And Mimi. And Sabina there. And Simon, Thomas, Valerie, and Veer. So we are missing Jaden, Jonah, Kate, and Lucy. Excellent. Okay. How many electrons, Francois, in calcium? You don't have a period. No, do not take his periodic table. You get another one that's free. You can keep it. You're welcome. I now name you Squirrel, after the forest creature that just died to provide you something that you lost. We killed the tree for that. Senior courses now. Forest creatures are dying right, left, and center. How many electrons? How many electrons? 20. Excellent. 20 electrons. And before, we would go Bohr. So let's do a little familiarity. We go 2. How many in the next shell? 8. How many in the next shell? 8. And then how many left over? 2. So let's compare that. We're going to compare that. Number 1, electrons don't like each other. So if they have the same, they also don't like to work. This is literally the amount of energy. This is climbing uphill. So this is potential energy in the same way that climbing uphill is potential energy. If there's room down below, they like to fall. But here's how you put it in. We have 20 electrons. You only can put 1 in a subshell at a time. And I'm going to draw them with these arrows because of something called the Pauli exclusion principle, which I just mentioned of why we don't go through. Electrons have a property called spin, which you can think of as spin. It's not, and I'm not going to explain it. But they like to be the opposite. How many electrons fit in a suborbital? 2, so I can only put 2 in that one. They don't like to climb uphill, so one will go in, and then the other one will go in as the opposite spin. How many will fit in here? 2, so we'll do it again. How many will fit in here? 6. And they're all the same energy. So this is like you go into the washroom, whether it's a lot of stalls or a lot of urinals. Do you pick the one right next to someone else? No. Far apart. So they first go in and they separate. Now, it doesn't matter from the perspective because we're going to fill this up anyway, but just to show you how you do it in case you were ending here. They first separate, and then they don't want to climb up, so they fill up. And I'm making sure the spin is the opposite every time. That's how I denote different spins. If you want to know how they got that, they took an arrow and they cut it in half. And now that's an up arrow, and that's a half of a down arrow. And that's why that particular shape denotes spin. To show that they have opposite spins. This will never happen. Electrons hate each other. That's the force that's actually keeping us apart. Yeah, I know. Now, we've got 2, 4, 6, 8, 10. Oops. 1, 2, same level. Now we fill up here. Now what's the next one to get filled? No, hands up 3D. Hands up something else. Woo. Beer. 4s. 4s is lower. So this is the right energy level. That's the next one. But 4s is the next energy level, and it's closer. So I'm going to go there. You live in Roger's house. You need chemistry help. You're supposed to go to see Mr. Neufeld, but Mr. Snow is right there. Closer. Less energy. I don't know if that analogy works at all. So what are we at now? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Perfect. Now, what did we get out of this? 2, 8, 8, 2. It corresponds to Bohr. It works. This is one energy level. This is another energy level. That's another energy level. Then we have that one. Notice I said it's 2, 8, 18. It is 18, but those two will fill up first. And that's why we separate them out. That's why Bohr found this separation, even though it doesn't correspond to the energy levels. That 3D is in this energy level, but doesn't get filled up first. So 2, 8, 8, 2 to take it back to Bohr. Now, I was following some particular rules as I filled them up. Object if I'm going too fast. Electrons are filled from the bottom up. Electrons are separated in the same suborbital until they must pair. And when they pair, they use opposite spins. I wear shorts and a t-shirt. I was just thinking as you said that, I got to take my lab coat off. Yeah, and, well, if you're feeling like you're suffocating, tell me to open the door, because air is kind of important. And stale air is a thing. There's a lot of research that goes into making cars because you don't want them airtight, because then people would die. However, people don't like sound, and every time you make it not airtight, they get more sound. And people like quiet cars. Yes, Lillian. Oh, why? Because it's lower in energy. What? That's a silly question. It is lower in energy. Pardon? Well, the because you're asking. Here's the mountain that you've been asked to climb. 1S, 2S, 2P. No, let's start higher up. I'm gonna run out of room. And that is, we'll start with 4S, 3D, 3P, 3S. You are climbing this mountain. And as you make your way to the top, this is a terrible, terrible drawing, and I do apologize. I just got this. And on your way to the top of this mountain, you notice there's another peak. It is closer to you than that peak. This is on your path. That's the right path. But this is the 4S peak, so you just make a detour and you stop there first. It also helps. What? That's not the same shell. Yeah. But they have different shapes, and so they have a different energy. Notice even within the same shell, the suborbitals themselves have different energy. So the 2P has more energy than the 2S. They are more difficult shapes, if you want to think of it that way. And so the electrons fill up the S first. That's nice and easy. Nice big round, they just pop right in. But then like, oh God, the only thing that's left, and this is partly like a packing problem, and I don't want to, it's not packing in the way it has to be efficient, but you can think of it a bit like that as an analogy. You have to fit all these orbitals together, and the S and the P's fit together. They undergo a thing called SPD hybridization, which we're not going to get into, but it means that they go together. So when they do that, then they fill up this one. Then they go to the next one, they do the same thing. Turns out when they do this and they do that SPD hybridization, they all fit together. The next energy level that is an S, that is a sphere that's easy to go into, just happens to be less energy than the next energy level here. But it turns out this energy level, because it's the next one for here, is lower than the next P. So it'll fill up a sphere, and then all the butterflies, and then the dumbbells. And it is like filling water from the bottom top. These are all the, it fills in order. If you're asking why is that peak lower than that peak, it's because that's the way it is. It's a bit like when you're hiking, why is that mountain lower than that mountain? Because that's the way we found it. So this has been determined experimentally, and now we've made math to fit it. But we didn't predict that. That happened to us. Yes, and then yes. Oh, you're just stretching? Oh, no. No. And the reason I know that is I'm going to show you a trick later involving this periodic table. But you can think, because when you fill it up, this is the S, right? The first two, 1s2. You got 2 electrons in the S. And then we put 2 electrons in the S. It's 2s, second level. The other one is the P. There's 1, 2, 3, 4, 5, 6. So we fit 6 electrons in the p orbital. Then we come back and we're starting over again with the s, and we fit 2 electrons there. And then we have another p orbital. Then we fit in the 4th level 2 electrons, but then we fill up the 3D. 10 electrons fit in there. Our periodic table mimics the quantum electronic structure. Remember I showed you how Bohr mimicked it? It's actually because it's mimicking quantum, which translates into Bohr, because Bohr is just a poor quantum model. And when we get through, it turns out this is F. We would have to find elements larger than down here to get into orbitals that are different. And we haven't run out of F yet. So the answer is we just haven't made, there's no atoms made that need it. There may be theoretical ones, but yes? Yeah, so the next one, we would then go to 3D, because that's the next one. It's really close in energy levels. And then we would go to 4P, and then 4D. Oh, 5S, sorry, 4P, 5S, 4D, yes. Thank you for catching that. Pardon? Yes. We will do a lab, but not now, because a quantum lab would be like drawing the orbitals. Yes. Yep. Sure. No. Well, it's not spin. And I want to make sure I don't mess this up. Because, and it's not magnetism, even though those have, but it is angular momentum, so it's very much like spin. So you can think of it as spinning on its axis, even though technically we treat it as a wave for a lot of the things with the statistical calculations. So if we treat it like a particle, you can think of it as having spin. It has angular momentum without having true spin. I don't know how that happens. It just does, because we're dealing with tiny things. So I just like calling it spin and just moving on from there. Well, you are, but at any level of science, like here we are, grade 11 chemistry. You have reached the boundary of our knowledge. And I'm sure if I brought in a professor from quantum chemistry, he'd explain it way better than I can, and he would tell you lots of things. You probably need more chemistry to understand it, but he would know a bit more. But we are at the edge of what we know, which is kind of exciting. If you go into chemistry, you can find out more. Do some experiments. Is everybody good with this? If you've ever, I was going to say had a child, but obviously you would hope, not hopefully, if you have one, great. But if you've ever babysat a child, you know that very quickly their why questions will get you to the edge of human knowledge. And you can do that really fast. Okay, you're going to need some of these. Oh, you have to draw it in. Because I want you to give me the electronic structure. Now, you only have to draw it once more, because we're going to do it for carbon. What did I just, stop it. And I'm going to show you notation such that we don't have to draw this every single time. But you need to be able to draw it from memory with the right order. And then after, I'm going to show you how to a trick on how to do that. really is just a trick. We just did calcium. Let's not do calcium again. I promised you I'd only go up to the 4F. So we could get up to 1, 2, 3, 4, 5. Oh, let's do strontium. Strontium and krypton. Now, once you have this, it would be helpful if this one piece was in pen. Only reason you're going to do pencil work on top of it and erase it. Yep. That is 7 on 4F. There are 7 F orbitals. It's exciting. And then I should probably lock that down. And it probably wouldn't be fair if I said, someone come up here and do the first one. However, I am going to have someone do the second one and the third one and the fourth one and the fifth one. Just come up here and write it down. Yes, yeah. Well, it always says bonus material if you work ahead, but keep in mind when I say bonus material if you work ahead, if you understand it, there's some students who come from like weird countries like Germany, and they do some of this in like previous grades. Weird countries. However, there's also some students who come from places like the U.S. and they've done no chemistry at all because they did all the biology. And then other countries, they have done some sections and not others. So hands up, I think over here, yes. Oh, we're going to do. I'm going to do but you don't know how you're going to do them yet. Okay. I can't see that from here, but just let me do carbon as an example. Okay. So you're not just make sure you have this written out in pen. No, you're going to do it and then erase the pencil marks over top, and then do it again on the same one. Yep. Yep. And really, at this point, if you go like this, for rough work, oops, you're going to be fine because we're just going to count. But the Pauli exclusion principle means they need to have that would blow up. The Pauli exclusion principle means that they have to have opposite angular momentum or opposite spin. Yeah? How do those what? Oh, those are just exothermic rapid gas combustion reactions. How a gun works is that you do a chemical reaction that releases a gas, and the gas fills the chamber and fires a projectile. Most explosions are just producing a gas really fast. That moves all the metal material, if you're talking about a weapon, that then goes through people like bullets. Oh, nuclear missiles. And if you get enough material in the same spot, it undergoes fission, and then nuclear radiation is given off. Fission. That's it. Yeah, we're not doing nuclear chemistry, but you just need enough material. So they'd make a bomb with less material and an amount to make it enough a little too far away. When the bomb hits, it just joins them, and then it goes boom. It has nothing to do with this. No, you're using unstable atoms in which their nuclei it's a chain reaction thing in which particles hit other particles and cause them to break down, and when you have enough of them, you get so many events happening at once that all of it goes essentially at the same time. So it's a chain reaction process, not an orbital. I mean, orbitals are involved in nuclear chemistry, but this doesn't make them go bang more. Okay, carbon. How many electrons does carbon have, please? Thomas. Yeah, in carbon. 6. So we got 6 electrons, and so I'm going to go 1. Now I'm going to do this in pencil. 1, 2, 3, 4, 5, 6. And then I'm going to write this out as I would write it on a piece of paper. What is the electronic structure for carbon? Now you can make a little table that has electronic structure and carbon, so let's do that. I think I have it already partially set up down here. No, I don't. Let's do that. Let's go element electronic structure. And instead of going 2, 4 as we used to do, carbon is in the first energy level, which is S. Its sublevel, it has 2 electrons. In the second energy level, it has filled the S with 2 electrons. It had then continued in the second energy level with P, and it had 2 electrons. So the electronic structure for carbon is 1s2, 2s2, 2p2. So when we say electronic structure, did you have your hand up? Corner of my eye? No? We now say this. And then I go, let's erase this. And do the next one. Ne. And then Mg, and then S, and then Sr. And we're going to go down and do the electronic structure for all of those using this as our guide. Yes? You've done them all? Nice. Did you do this last year? Oh, okay. And let's call some people up. So you should have that drawn, so I shouldn't have to do it. So neon, magnesium, sulfur. Let's attach some names here. I'm not even going to look. I'm just going to say, Simon, you're on the first one. Well done. And let's go with, oh my God. It picked you as the second one, but I won't do that. Sabina, you're on magnesium. And then Davis, you're on sulfur. Sulfur, after strontium and crucium. And I will leave the last two to do afterwards, so everybody still has the idea. Oh, I could still be. You won't be disappointed that you haven't been called upon yet. That would be hugely disappointing, I know. Let's put some lines in here. Excellent. Any of those first 3, as soon as you're ready, come on up, grab a pen. Write them out. Oh, not that pen. That pen. Yeah, you can pick your color. Oh, click on that because we don't want the line drawn. Oh, no, you have to click here. I do that. I used to have a pen. There you go. Pick your color. And then go. Oh, but you have to still do it on there. I used to have pens that worked on the projector. I just don't anymore. Oh, you have to do it on there. I know. Oh, you tried to edit it. Oh no, what you did is here. I'll get rid of that afterwards. What you did is you pressed one of the buttons, I think. Anyway, press on the yep, you should work. Your hand can still rest on the screen. It's not that. Hold it. Why is it 2P2? Sabina, check your work. I think you might have copied me in some way. Sorry, what? Oh, I'll help you. Yeah. But how many electrons does sulfur have? Okay. Have you put them into your diagram, filling it up as you go along? But do you have the diagram? Bring it on up. No. You have 2P2. How can you have 2P2? Oh, that's yours. Sorry, I was looking there. Yes. Yes. Simon's is good. Simon's is good.
So I have my
Right. Right. Pencil. So how many electrons does sulfur have?
16. On the other side, I have it.
1s2, 2s2, 2p6, 3s2, 3p3. And, oh, yep, there you go. 2, 4, 6, 8, 10, 11, 12. Does sulfur have 12? No, 16. Oh, you have to keep going.
Yeah.
Yeah.
Then now do I go to?
So how many electrons does sulfur have?
It has
16. So you go 1, 2, 3, 4. But your 2p here, you don't have 3 lines. Right? So I have figured out the error, and I'm going to ask if anybody else has this. The number of dashes here, and this is a good point, so fix that. Oh, yeah, I'll give you your pencil back. If you just put one line for the P, you need 3 separate ones. How many does each one fill in terms of electrons? 2. So you need 2, 4, 6. Each one of those is a different orbital. So in the D, you need 1, 2, 3, 4, 5 to fit the full 10 that fits there. So make sure you have these spacings. You haven't just labeled the energy levels, but you have in-betweens, and you do a little erasure there. And then, who else? So, oh, and Sabina looks great. While we're waiting, let's get someone on to strontium. Heather, can you do strontium? Just, yeah, come on up. It's exciting. It's exciting. It's very exciting. And there's a pen right there. Someone take my other pen. Where's my other pen? Oh, okay. Fair enough. Oh, yeah, it is. You can rest your hand on it. Just don't touch the buttons on the side because they'll start typing. But it's not a touch screen. It's a pen only. So you can rest your hand on it like paper. Excellent. Yeah. Yeah. Oh, hold it. Yes. Sorry. I thought your 5 was an S for a second, but it's good. Yep. That's 5S2. 5S2. And Krypton. Oh, David's coming out. 2, 4. That should. How many should the P have in it? No. Because it has 3 slots. Every slot fits 2, just like you're doing the S. Yeah, so when you fill it up, you go 1, 2, 3, 4, and then you go 5, 6, 7, 8, 9, 10, because now you put and that P should have 3 of them. That should have 5. So fill it up with 2 electrons each. And krypton, Valerie. And what? Where's the thing? Excellent. You want me to see it, or are you just good? 1s2, 2s2, 2p6, 3 and 3p6. Sulfur. Yeah, if that's what you're saying, that's perfect. And while you're doing that, for everybody else, oh, sorry, I thought I could type while you were doing pen stuff, and I can't. So hit the pen button. There, you go. Not group, not student. Excellent. And before you begin, Valerie, I'm going to just do one thing. Don't start yet. I'm just going to do one thing. Because I am going to tell everybody else. Okay. Students, portfolios. Okay. Okay. There. You can begin. Just hit the pen to make sure it's on your screen. There you go. I've just posted to Class Dojo an activity. Take picture of all of your examples. So your set, I would like to see your electronic structures. If you could take a picture and upload them on Class Dojo. Yep, your completed set. Because it's not fair that only the people I called get to come up. And we are, hold it, what's today? Wednesday? Oh! You can take the picture after did the bell go? My apologies. I should have been keeping better track. So that's the last thing. From last day, if you're still like, there's a lot of confusing things, there is an order, and this is really not math, even though it has a lot of numbers and letters. This is labeling what we observe. Your examples of these. So I want your examples uploaded. I want to see your work. Yep. Oh, how many of you do not have a Class Dojo because you're not logged in? No, but you've logged in, right? Yeah. I can give you your own personalized QR code, Simon. Yeah, I can log you in later. Given you have to run to another class, it'd probably be unfair if I said do it now, because I'd have to get it loaded. But yes. Kaylee, can you get it on your phone? It'd probably be easier for taking pictures. If you, Simon and Kaylee, if you want, if you email me, I will email you your personalized QR code. And that will allow you to log in on your phone really easily. Not now, because I have another class coming. I was starting to add them up, and then because we have to report on proficiencies, I'm actually getting a whole new grade book that's I'm going to do with the spreadsheet, and I'm not going to use Google Classroom. So I just haven't put the marks in yet. When today?
So, are we not going to see it for this day?
Not today. However, I am hoping to email you the marks today.
Oh, okay.
Yeah.
Thank you.
Yeah. You're welcome.
Sorry.
No, that's okay. Why are you returning this? Oh, fair enough. Okay. Save paper.
We don't have a test on Friday, right?
Not this Friday. No. At the most, you would have a test next Friday. Because I'd want at least a class in between for doing it. Yeah, you're welcome. No.
About these ones.
Yeah. Oh, I haven't added those to the class yet.
Yeah.
You can't do them. Because I just haven't added them. I could. I just don't remember to because we're not there yet. You.
Yes, this is about
Yeah.
electronics.
If you want to email me, I will limit you to once a day. You're allowed to email me to bug me to say put Kia on, add them to our class, and then you'll be able to do them. You're allowed. Fair enough.
The most you get is like 10.
Okay. But if anybody has their Hebdens, I put them back in the Hebden shelf. Hello. Ready to write the quiz? Ready to write the quiz?
Can I do it during prep and stuff during the class?
Can you do it what?
Can I do it during prep and stuff during the class so that I can?
Do you know where the testing center is? You can do it tonight in the testing center.
I don't know what the testing center is, so.
You go. How do you go to the testing center?
You talk to your duty staff and say, hi, I need to go take a test in the testing center. You write on the board and it's at the top of the stairs. I'm at test, your name, at test, or testing.
But where is it physically?
And then you walk 2 Ross down here into this classroom.
Is it this classroom this year? Oh. Was it? I had no idea. I didn't teach in this classroom last year, so I guess I didn't pay attention. Yeah. So, you can, but it's only on Tuesdays and Wednesdays, right? Only Tuesdays. What? What?
Math, I have no idea. I thought it was testing. I only took one test